Welcome to all of you, my students. Today we are going to discuss about the functional organizations of instructions in IBM System 360/91. This topic is related to MSc Computer Science 4th semester, Paper 3, Advanced Computer Architecture, Unit number 4, Advanced Processor Technology. This tutorial prepared by me. I am Suresh Kumar Thakur, Asst Professor, Department of Computer Science, Indira Gandhi Government Arts and Commerce College, Vaishnagar, Bhilai. Introduction to IBM System 360 Model 91. The IBM System 360 Model 91 was announced in 1964. Functionally, the model 91 ran like any other large-scale system of the 360, but the internal organization was the most advanced of the System 360 line, and it was the first IBM computer to support out-of-order instructions executions. It ran operating system 360 as its operating system. It was designed to handle high-speed data processing for scientific application. This included space explorations, theoretical astronomy, subatomic physics, and global weather forecasting. The CPU consisted of 5 autonomous units: instructions, floating point, fixed point, 2 storage controllers for the overlapping memory unit, and the I/O data channel. The floating points unit made heavy use of instructions pipelining and was the first implementation of Tomasio algorithm. It was also one of the first computers to realize multi-channel memory architecture. The IBM System 360 was introduced in 1964 as the fastest, most powerful computer then in use. It was specifically designed to handle high-speed data processing for scientific applications such as space exploration and physics, global weather forecasting. IBM estimated that each day in use, the Model 91 would solve more than 1,000 problems involving about 200 billion calculations. The system's immense computing power resulted from a combination of several key factors, including advanced circuit that switched in billionths of a second, high-density circuit packaging techniques, and high degree of concurrency of parallel operations. Now, just technology about the system component. The major component of Model 91 are an IBM 2091 processing unit, IBM processor storage model 1 and 2, IBM 2860 selector channel, IBM 2870 multiplexer channel. Instructions processing. The 4 possible processor storage combination in the Model 91 are termed K91, KK91, KL91, and L91. They differ in the number of types of processor storage unit used with the 2091 processing unit and in the way the processor storage units are attached. The 2395 Model 1 is interleaved 16-way and has the capacity of 2,97,152 bytes. The 2395 Model 2 was interleaved 16 ways, has a capacity of 41,94,304 bytes. Instruction processing. Is the main key portion of our today's lecture. because we are going to discuss about the functional organization of instructions. This is the instruction processing, how the IBM 36091 process the instructions. In the IBM 2091 processing unit, this one 2091 processing unit is the channel processing unit for the model 91. Physically it consists of 5 stand-alone units, one processor, 2 CPU power supply unit, 1 power distribution unit, and maintenance console. This is the diagram of IBM 36091 logical element. Functionally, the processing unit consists of the following major logical element: the instruction processor, the fixed point and the variable field length execution element, this one, the floating point execution element, this one, the main storage control element, and the peripheral storage control element. The instruction processor may be considered the major coordinating element in the model 91. For each instruction, it determines what must be done and which execution unit has responsibility for it. Branching, status, switching, and I/O instructions are handled by the instructions processor. Other instructions are routed to other areas for further processing. The fixed point, variable fixed field length execution element contain the general register, which are used also by the instructions processor. Functionally, this element operates as an independent stored program computer. It has its own instruction stream, its own execution circuit, and a set of operand buffer. The floating point execution element operates as an independent computer, although most of the floating point instructions require more than one cycle of execution time. The main storage control element handles all fetching and storing of data for the CPE. It is designed to minimize conflicting requests for storage and to make the most efficient use of storage. The peripheral storage control element handles the transfer of information between the main storage control element, extended main storage, and input output channel. So this is the brief discussion about the logical element of IBM system 360/91. Instructions processing. The primary function of the instruction processor are the fetching and buffering of instructions from storage, the fetching of required operand, the issuance of instructions to the appropriate execution element, the handling of interruptions, the execution of all branching, status, switching, and I/O instructions. The instruction processor has an instruction stack of 8 double words, a set of 3 instructions control register, a set of alternate instructions buffer register, totaling 2 double words, a decoder, and a 3 input adder for the generation of effective addresses, which we have seen in this diagram. The instructions processor uses the general register situated in the fixed point variable field length execution element. Instructions fetching. Instructions fetched from the storage in the instructions stack of the instructions processor. The fetching mechanism operates differently under each of the 3 conditions. Initialization, normal operations, recognition of discontinuity. It is governed by the three control registers: instruction register, upper bound register, and lower bound register. Instructions fetched from the storage are stored in the instructions stack of the instructions processor, as instruction stack is used for two peripheral reasons. First, to minimize storage access time for instructions fetching, and second one is to reduce the number of instructions fetches required while the program is executing a tight loop. The instruction stack normally contains the current instructions double word and the next three double words. By keeping a number of double words ahead, the fetching mechanism is able to fit instructions fetch into slack period between data fetches and store. The fetching mechanism operates differently under each of the three conditions: initialization, normal operation, condition of discontinuity. It is governed by the three control registers which we have seen there. The instruction register points to the instructions currently being decoded, and the upper bound register to the most recent double word brought into the stack, and the lower bound register to the earliest double word present in the stack. Initialization. We are going to discuss about the initializations. Initially, the instructions stack is empty. When instructions fetching is initiated, the main storage address of the first double word of instructions is set into the upper bound and lower bound register. Part of the address of the first instructions is set into the instruction register, the upper bound register, which controls the actual fetching of double words of instructions. Bring the first double word into the instruction stack. As each instruction's double word is fetched during initialization, the upper bound register is incremented until any of three conditions occur. The address in the upper bound register is 4 double word higher than that of the instruction register. Second, a branch instruction is decoded that set coordinate conditional mode. A discontinuity is recognized. When instruction stack is full, initialization is completed. Normal operations. During normal operation, the instruction fetching mechanism continually attempt to fetch double word. Fetching will not take place if any of the three conditions just described in presence. When incrementing of the upper bound register would cause the three low order bit of that register to match the three low order bit of the lower bound register, both the upper bound and the lower bound register are incremented. Discontinuities. A branch operation interruptions or stored into the instruction string may cause the disruption in fetching. Instruction issuing. In addition to fetching and buffering instructions, the instruction processor fetches the required operand and issues instructions to the appropriate executions element. On each machine cycle, the instruction processor checks for interlock. If there are none, the instruction selected by the instructions register is decoded. Decoding is the first of three possible stages in the issuing the instructions. Stage 1. Decoding. During decoding, the following is determined. First, the type of operation to be performed. Second, whether the operation stack for the appropriate execution element can accept the operation. Third, if a storage operand is required, whether a buffer register in the appropriate execution element is available to receive the operand, or if a store operational is specified, whether a store address register is available in the main storage control element. Fourth, If an effective address is required, whether the 3 input adder and general cache register used in generating the effective address are available for use. Stage 2. The operands are routed. If the address generation is required, the pertinent operands are routed to the 3 input adder. If the instruction is a store, a quick check is made of the effective address, and if this check indicates a possible store into the already fetched instructions stream, processing of the instructions at stage 1 is stopped until the processor determines whether the store is actually into the instruction stream. If it is, the processing at stage 1 remains stopped until the process has issued a fetches to store for the instructions double word affected. Stage 3. The effective address of the storage operand is passed. At this stage, the effective address of the storage operand is passed to the main storage control element. If a fetch operand is specified, the address of the buffer register to which the operand is to be sent is also specified. Execution of branching instructions. Decoding a branch instructions are determined by the type of branch instructions to be processed, the availability of circuitry for processing, and the following: whether the instructions processor is in conditional mode, whether the instruction processor is in loop mode. If loop mode is established, whether current instruction is that which define the current loop, whether the current instructions is in the target of the execute instructions currently being processed. Normally, when a branch is taken, the targeted address of the branch is set into the instructions register, and the upper bound and lower bound register and instruction stack are adjusted as required. When a conditional branch is encountered and loop mode is not set, the instructions processor operates as through either direction could be taken, but assume that the strongest possibility is that the branch will not be taken. Conditional mode. Conditional mode is established. Conditional mode is established when the instructions processor executes a branch on condition instructions for which the condition code is not yet determined. When conditional mode is set, no additional instructions fetch are made. The instructions processor continues to the decode instructions, generate addresses, and issue operations to the fixed point and floating point execution element. The instruction processor continues to decode instructions conditionally until any of the following conditions occur: the condition code is set. Second, the instructions are available in the instruction stack. The operational stack of the fixed point or floating point execution element is full, and instructions to be executed within the instructions processor is decoded. Now let's move to loop mode. Whether a branch backward is taken to a target fewer than 8 double words back from the current address in the instructions register, loop mode is entered. When loop mode is entered, the loop is locked into instruction stack, and as a result can be executed repeatedly without fetching of the instructions. During loop mode, if there is no data fetched or stored to be made, an instruction double word is fetched every cycle until the instruction stack is full. If data fetches or store are to be made, instruction double word fetches are made every other cycle. Execution of other instructions. The instructions processor execute all status, switch, and IO instructions and plays a large part in the execution of multiple operation instructions. When one of these instructions is processed, the instruction processor usually does not issue any succeeding instructions until its part in processing in the first instructions is completed. None of these instructions executed while conditional mode is set, and many of the instructions require that all instructions being executed. When that instructions is decoded to be completely prior to its execution, the instructions requiring this completion of other instructions are the 4 IO instructions and load PSW, supervisor call, set storage key, and set program mask. This is the reference. This reference has been used to make this tutorial. IBM System Reference Library, 4th edition, IBM System 360 Model 91 Functional Characteristic. Thank you very much.